So we were talking how you got an object going around, got a mass, maybe two masses on a massless rod or something rotating around. This is M1, that's M2, R1, R2, and we'd said that kinetic energy of one mass going around 1/2 mv squared. So the total kinetic energy be the combination. They've got different velocities if they're different r's because v equals r omega, but they're all the same omega. So we could write this as the kinetic energy is 1/2 I omega squared, where I was the sum m sub I r sub I squared. And so we had figured that out, and then we realized, wait, this I thing actually turns out to be useful because we found that I shows up in lots of other equations where we used to have an M. And so in all kinds of equations for rotational dynamics, wherever we had an M before, we now have an I. And it's the summation of mr squared. And so that makes it a useful quantity to study. And we'll see more about this later. But the just keeps coming back. Most physics books refer to that quantity I as the moment of inertia. I have occasionally seen some engineering books refer to it as the rotational moment. Your textbook refers to it as the rotational inertia. All three terms actually mean the exact same thing. They are all that I sum mr squared. And so that's what we're looking at. Now I've seen one book, which is because all three terms are used interchangeably. I've seen one book, and only one book, actually refer to it as the rotational moment of inertia. Okay, because then no one can seem to figure out what to call it, so they just called it everything. All right, now the problem that you run into is if you have an extended object and you're trying to make the extended object rotate. Because now you have a problem that it's not a discrete set of quantities. So you have this extended object and you're trying to make the extended object rotate some omega. And so each little piece of this object is going to be a different delta m. Okay, so we're going to have to add up all of those r squares delta m. So r squared delta m, okay, r sub I, m sub I, so each one of these is potentially a different r. Okay, and so I is going to be the sum of that. Now, the smaller these little pieces get, the more accurate it's going to be. So we want to take a limit as the delta m's get really, really small. And so what that gives us is an integral. So we end up with I being integral of r squared dm. Okay, now that sounds cool. So dm, what do we mean by dm? So we have our object here, and we have a little dm up here. Well, we have to integrate over all the dm's that are on here. Well, all the dm's are in different positions. So what you're really integrating is position. Well, how does dm relate to position? Because you have different positions. So what you have to think about it and say, well, how does m relate to position? And we know that m divided by volume is density. Okay, so m is going to be density times volume. So we think about it and say what it would be a differential version of dm. Well, the differential would be rho dv. So now we say, what is dv? Okay, dv is this differential volume. So the differential volume would be, if I have a little piece of volume right here, I got, some little dx, some little dy, and some little dz. So dv is going to be dx, dy, dz. Okay, so now we start putting all this together. And so we would say, therefore, that I is this integral of rho dv, which is dx, dy, dz. Well, r squared rather. Okay, times that. Well, wait a minute. We're integrating over three different things, so we have to have three integrals, one over each one. So now this is equal to integral r squared rho dx, dy, dz. This is a triple integral. So this integral right here is over dx. So you do the integral over dx, and the next integral is the integral over dy, and the final outside integral is the integral over dz. But this is your general form of the moment of inertia or rotational moment. It is this integral r squared rho dx, dy, dz. All right. Now, the problem is this is a triple integral. So I'm going to do an example of that next just to show you how that works. And then I'm going to show you a way to avoid doing a triple integral. Because always, the best way of doing a hard integral is to avoid it if you can.